All right, welcome back to our lesson on gravitational fields. So today, the goal, I can explain the concept of gravitational fields, and then I want you to be able to calculate the strength between two masses. So what are we looking at today? First thing I want you to, as a reminder, is the difference between mass and weight. These are the two words I said. They're used interchange. In society, people use these and they interchange them, and they shouldn't be, because there's two differences here. Mass, first of all, is a scalar. And it indicates, or it's a measurement, I guess we'll say, a measurement of the amount of material in an object. So this would be weighed in terms of, or you'd be measuring in terms of kilograms. If we're looking at weight, weight is a scalar. And that is a measurement of the force acting on an object. So measured in completely different units. Yes, they are related, mass and weight, because you need mass to calculate weight, but they mean two different things. So mass is how much material makes up the object. Weight is how much gravity is acting on that particular mass. It's measured in newtons, so it's a vector. Force of gravity in space. We always hear people talk about weightlessness and zero gravity. Zero gravity is very, very hard to achieve, and I'll explain the why here. Earth, we know, emits a gravitational field. So if you are floating in space, naturally, you would want to fall back to Earth. Okay, that's your attraction force due to gravity. So why do astronauts experience what we call weightlessness if Earth is pulling them downward? Well, there's a couple of factors. I'm going to leave some of them. I'm going to oversimplify a couple things here. What else do you have out there? You have your moon. You have, maybe we'll put Mars way over here, and then you have the sun over here. And like I said, I'm going to do an oversimplification. What happens as you move away from Earth, two things happen. We're going to talk about the why. First of all, the further you are away from Earth, the less pull it has. Okay? So as you move as an astronaut, leave the Earth's atmosphere, gravitational attraction is decreasing, and we're going to talk about why in a second. But as you approach the other objects out there, the moon is going to pull on you a little bit. The sun is going to pull on you a little bit. Mars is going to pull on you a little bit. So you have a whole lot of forces due to gravity applying to that body. So when you are out in space, the sum of force due to gravity is equal to Fg Earth plus Fg Moon plus Fg Sun plus etc. And they essentially are approximately equal to zero. All right, so the sum of the forces are approaching zero. Now, do you ever experience true weightlessness? Do you ever experience absolutely zero gravity? And the answer to that is no. There will always be some amount. Now, our bodies can only detect a very, very minimal amount, and the less gravitational force acting on it, the less is noticed due to the naked eye. So a couple of things are playing a role here. So force of gravity in space decreases because you're further away from the planet. So let's talk about some of the forces at a distance first of all. So let's talk about that concept for a second. So I said that if you're on Earth, force due to gravity decreases as you move outward. Now we know that force at a distance means that there's no contact required. Okay, so force at a distance means that no contact is required. All right, the Earth does not have to touch you in order to exert its gravitational force. On Earth, if we stand on Earth, we experience an average of 9.81. If you move to a certain height away from the Earth, you would now experience less gravitational pull. As we move outward to another altitude, another height, it would decrease again. These are called what we call field lines. And field lines represent a region where a force is equal. So anywhere on that blue dotted line that I'm pointing to, and I'm going to do it in green, if you were anywhere on this dashed line around the planet, then you'd be experiencing the exact same gravitational pull. So these field lines emanate outward from the Earth. Now, these field lines are a graphical representation. You would not see them. And to indicate that it's a stronger force, the closer you are to Earth, the closer the rings or the field lines would be. And that's how we graphically show the closer you are to Earth, the stronger the pull. All right, so that gravitational field, it's like a region of pull. So as you approach the Earth, the gravitational pull gets stronger and stronger. Okay, so that's what it would look like in terms of a diagram, or how we graphically represent that particular scenario. So let's talk about what factors affect force due to gravity. And I've already mentioned one. The first one is distance. So distance between objects. What's the second factor that plays a role here? And although I can't see hands up, I'm sure everyone's screaming the answer. It's actually mass. Mass of objects. So this is where I do a very interesting demonstration, and I'm doing it right now. I'm holding out my pen, and when I drop the pen, I'm asking myself, why does it drop to the Earth and not towards me? Okay, I'm not exactly a small individual, so why does the pen not get attracted to me? Why does it prefer to fall towards the Earth? Well, the Earth is far more massive than myself, so the object that has more mass will definitely win out, which is a good thing, because if you're walking down the street and cars exerted a gravitational force, you'd be constantly fighting against that, and you don't want pebbles coming flying at you because they're attracted toward you due to gravity. It just sets up a bad scenario. So it is good that the Earth is the overlying major mass here. So formula that arises from that. On Earth, we use Fg equals mass times g, and we approximate g to be 9.81 meters per second squared. That's an approximation because it depends on where you are on the Earth. If you are in the lowest point or at sea level, it'll be different than if you were in the top of the mountains. So how is g calculated? Well, Newton did us some calculations, and what he found was there was what we call an inverse relationship, that the relationship between masses is directly proportional, and it's inversely proportional to the distance between. All right, and there's a governing factor, there's a coefficient that needs to go in there to make sure everything works out for us, and that's a capital G. So what is our legend? So G, small g, is our force due to gravity. Force due to gravity. Capital G is our universal constant, universal gravitational constant. And that value is 6.67 times 10 to the negative 11. And the units, and if I recall it from the top of my head, would be, I think it's meter cubed per kilogram second squared. All right, so there's our universal gravitational constant. M1 and M2 are just masses of the objects, so mass of objects. And the r in the denominator is distance between centers of objects. All right, so there we are. So there is our calculation. And if we look at the formula itself, and if we look at the radius of the Earth, so I'm just going to go example right here. If we take our formula and we do 6.67 times 10 to the negative 11, and we can go through and do the calculation for an object at a given height. Now, I'm not going to, it depends on the person here, so usually I take a person, but that formula then, so rather than erasing everything on you, g m1 m2 over r squared equals 9.81 meters per second squared, will also give you, will also give you 9.81 if we look at it in terms of the Earth's surface. Sorry, kind of losing my train of thought here. So, so that will calculate your gravitational value. And sorry, I've lost my notation here. This is actually force due to gravity. All right, this is not calculating gravity. This is actually the force due to gravity, Fg. That's my mistake. I apologize. I'm getting my formulas mixed up in my head here. So this is, and I even wrote it there, which is the funny part. And this formula calculates your force due to gravity. I just got my notation wrong there. So your force due to gravity, I did the example. If you were to use that formula, your force due to gravity is going to equal mass times 9.81 for you on the surface. So usually I take a person in the class to go through and do the calculation for, but it doesn't work as well this way. But that's what it essentially comes out to be. So that's the formula. I've got a couple of examples to finish up this part of the note, but yeah, that formula calculates your force due to gravity. And actually I can finish up the next part quick here, because that gravitational field strength, remember in the previous slide there, I had those rings. And those rings are your forces at that level. So if we take that formula, force due to gravity equals g m1 m2 over r squared, and I divide out a mass, so over here for 1 second, if I had force due to gravity equals mass times gravity, if I divided both sides by your mass, all right, divided both sides by m, what we would find is we're just left with gravitational field strength, or G. So that's equal to G, all right? And that is our field strength. So for gravitational field strength, and this is where I was kind of getting ahead of myself, G is equal to, okay, G, and now I go to a capital M over R squared, and down here, capital M is mass of the source. And for us in grade 11, it's always going to be Earth. When we move into grade 12 course, we start doing other calculations. All right, so there is your gravitational field strength. So if I'm calculating G1 or G2, I'm going to use that formula there. And what that would give me is, it would give me a calculation of, this is how many newtons per kilogram this person was. So if you were 100 kilograms, you'd take your field strength and multiply by 100. This formula is far more important in grade 12. It comes up a little bit in the homework, and I just want you to be aware. So I got a couple of examples to finish up this note.